Hi everyone, welcome to the third video on vectors. We already saw how we can label coordinate systems and label vectors. We learned how length and distance is defined for vector objects. There's a whole bunch of other stuff we can do with vectors. And we'll next learn a little bit about multiplication involving vectors. There's different types of multiplication with vectors, unlike with numbers. If I give you two numbers and ask you to multiply them, like 4 and 5, there's only one type of operation you can do. There's different ways you can think about it. 4 times 5 means you have 4 groups of 5 objects, or 5 groups of 4 objects. But fundamentally, it's the same operation. For vector multiplication, there are fundamentally different types of operation that can be done with this new vector object. The first type of multiplication is called scalar multiplication, where you combine a number, like 3, and a vector, like v. And geometrically, what this operation does is it stretches or compresses a vector. Multiplying a vector by 3 makes it 3 times as long. Multiplying a vector by half makes it half as long. Another operation that we can do with vectors is addition. And addition only has one version, just like numbers. So adding two vectors together, u plus v, looks a lot like adding two numbers together, a plus b. We do have to be careful though with dimensions. We have to make sure that if we're adding two vectors together, they both better be in 2D, or they both better be in 3D, or both in 4D later on. So multiplication first. A scalar is the word that we're going to start using for numbers. So a scalar is anything on that number line, anything in R1. So pi, 3, negative 1/2, those are all scalars. 0 is also a scalar, by the way. This scalar multiplication, or multiplication of a vector by a number, is a multiplication that is performed on each component of the vector by that number. So you're just doing regular multiplication multiple times. So the definition of scalar multiplication is as follows. We have this letter C, which represents any number on the real number line. So C element R, that weird E-looking thing means element. So let C be an element of the real number system. And let V be any vector in R2 or R3. Then the scalar multiplication C times V is something that you get by taking the component V1, multiplying it by C, and taking the component V2 and multiplying it by C. And if you have a 3D vector, then you're also going to multiply the third component by C. It's best understood with an example. So here's an example on R3. We have u equals 1, 3, negative 2. Our scalar c is equal to 2, and we're asked to construct the new vector w, which is c times u. So w is equal to c, which is 2, times u, which is 1, 3, negative 2. Now our definition says that we have to take that 2 and multiply it into each part. So 1 times 2, which is 2, 3 times 2, which is 6, and negative 2 times 2, which is negative 4. And that's it. That's our answer. So it's normal multiplication done to each part. I mentioned in video 2 that there's an alternative for telling an alternative method for telling if two vectors are collinear. And it's connected to the following. If we multiply a vector by a scalar, the resulting new vector will always be collinear or parallel to the original vector. Now, if the scalar that we're multiplying is positive, then the new vector will be in the same direction as the old vector. If the scalar is negative, then it'll have an opposite direction. So if the original vector looked like this, so this was v, then the vector, let's say negative 1/2 times v might look like this. So it's half as long, and it's going in the opposite direction. I might as well draw a 3/4 v. And we'll draw another -1. -3/2 times v, which is 50% longer, 1.5 times the length. Another property of scalar multiplication is when you can create this new vector, it's going to have a different length. Unless c is 1, then it'll have the same length. But if c is not 1, it'll have a different length. And the relationship between the length of the old vector and the length of the new vector is as follows. If you take the new vector cv, construct it and find its length, you'll always find that it's equal to the old vector length multiplied by the absolute value of the scalar. So multiplied by the absolute value of c. In a different math course, this might be something that you do a proof for. So that would be math 1600. It'd be a fairly simple proof. Prove this is the case. Prove that the magnitude or norm or length of c times v is equal to absolute value of c times the length of v. But we won't prove it. You just have to take my word for it. The next part on the slide is really bizarre. We're going to accept this as a convention. We'll say that the zero vector is simultaneously collinear or parallel to all vectors, including itself. So it's collinear to everything, which means it points simultaneously in all directions, which is really, really bizarre, but we'll accept it. Okay. The next set of problems are operations based on those definitions of length, based on the definitions of scalar multiplication. So part A, review from the second video, find the length of u and the length of v. Just go through those again. So length of u, so double bar u, square root of 2 squared plus -2 squared. So the square root of 4 plus 4, square root of 8. So if this was a classroom, a hand would usually go up at this point. You'd say, are we supposed to simplify that? Are we supposed to write that as 2 times the root of 2? And the answer is no. Leave it as root 8. We won't simplify those. Same goes for rationalizing. So 1 over root 2 we'll leave as 1 over root 2. We will not turn it into root 2 divided by 2. So you may have been taught to do those types of operations in previous math courses, but they're not important for us here. Okay, next part. Part B, find the vector 5u and determine its length. So I'm going to say method 1 is the length of 5u is equal to the length of the vector that I get by multiplying u times 5. So 5 times 2, 10. 5 times -2, -10. So I'm going to find that length using the formula that we just saw. So square root of 10 squared plus -10 squared. So the square root of 100 plus 100, which is the square root of 200. Yes, that simplifies, but let's leave it alone. Method 2. Magnitude of 5u is equal to the absolute value of 5 multiplied by the length of u. Well, absolute value of 5 is just 5. And the length of u we found up above. We found it was root 8. So I'm just recycling. Even the arrow is green. So just 5 root 8. And these two answers are the same. How are they the same? Well, the square root of 200 is equal to, let's see, the square root of 25 multiplied by 8. Now, square root operations can be distributed across multiplication. So we can write this as the square root of 25 multiplied by the square root of 8, which is 5 times the root of 8. And it can be simplified further. We can write this as 10 root 2. The important takeaway is we have two different ways to calculate them. You either have to know both ways, or you have to be able to do conversions like what's shown up above. Okay, next question, part C. I'm only going to use method 2 here. If you want, you can use method 1, but I feel like using method 2. So the length of negative 2 times v is equal to absolute value of negative 2 multiplied by the length of v. Well, I forgot up above to get the length of v. I better do that. Oops. Length of v is equal to the square root of negative 4 squared plus 0 squared plus 3 squared. So the square root of 16 plus 0 plus 9. So the square root of 25, which is 5. So I'll plug that in down below. So I got a 5 for the absolute value of v, and for the length of v, and now absolute value of negative 2 is positive 2. So we get 10. And you could compare that to what you would get if you would simplify first. So create the vector negative 2v, which is 8, 0, negative 6. Then plug that into the length formula. So 8 squared plus 0 squared plus 6 squared. So 64 plus 0 plus 36, you get 100, and then take the square root, you get 10. So method 1 and method 2 are going to always agree, and you can see that they agree here as well. Now the last one, I feel like using that formula. I don't want to do it the long way using method 1, and especially because there are fractions involved. So the length of 1/2 times u is equal to the absolute value of 1/2 multiplied by the length of u, which is 1/2 times root 8, which can be written as the square root of 8 divided by 2. Or root 2. Since square root of 8 is equal to the square root of 4 times 2, which is root 4 times root 2, which is 2 root 2. And then you plug that in for the root 8, you get 2 on top, canceling the 2 on the bottom, so just a root 2. And all that stuff on the right hand side is optional. Don't stress this. Don't stress those types of manipulations with the square roots. The answer would be probably left as root 8 divided by 2. Okay. Now for a challenge question. Now for taking the definitions that we just saw and seeing how can we twist it and ask something a little bit more complicated. We're given a vector u, 5, negative 1, a vector w, negative 1, 4, negative 8, and we're asked to construct a unit vector in the opposite direction to u and a unit vector in the same direction as w. Unit vector has length 1. So I want a vector that has a length of 1 and is either in the opposite direction to the original vector or in the same direction as the original vector. How do we force this to happen? So I'll tell you what the method is. And you can experiment for yourself, convince yourself that this is always going to work. So our method is as follows. Step 1. Find the length of the vector. Step 2. Create a new vector. Well, I'll give the length a name. I'll call it L. Find the length of the vector L. Create a new vector V equals 1 over L multiplied by U. So method to create unit vector in the same direction as, I'll call it W, and I'll change this to a W over here. Okay, so we'll do that for that one. And method to create unit vector in opposite direction as U. Step 1, find the length L of the vector. Step 2, create a new vector V equals minus 1 over L times U. So opposite direction gets the minus sign. That's how you force the condition. So let's go and do these two operations, these two recipes to answer the question. So we're going to find the length of the vector W. So length of W equals the square root of negative 1 squared plus 4 squared plus negative 8 squared. So square root of 1 plus 16 plus 64. So that's a square root of 81, which is 9. Part 2 is the new vector V is equal to 1 over 9 times the old vector, minus 1, 4, minus 8, which we multiply that into each of the components. Minus 1 over 9, positive 4 over 9, minus 8 over 9. That's our answer. Homework. Confirm this is a unit vector. So make sure it has a length of 1. Confirm that this worked. Second part, creating a vector in the opposite direction to u. So this recipe begins again by finding the length of the original vector. So the length of u is equal to the square root of 5 squared plus negative 1 squared. So the square root of 25 plus 1, square root of 26. 26 does not square root evenly. Then we create the vector v by taking negative 1 over L, so negative 1 over the square root of 26, and multiplying by the vector u, 5 comma negative 1. So we get negative 5 over the square root of 26, comma positive 1 over the square root of 26, since negative times negative cancelled. And that'll be our answer for that part. And we would not rationalize the square root. We would leave the square root as it is in the denominator there. So we can state a component of the method that was just used as follows. If c times u is a unit vector, then it must be the case that the absolute value of c is 1 over the length of u. Let's take the approach that we just used to construct unit vectors in the same or opposite direction and use it to construct a new definition for collinearity. Two vectors u and v are collinear to each other if and only if they are scalar multiples of each other, that you can construct one by multiplying the other one by some constant, by some scalar c. So if and only if there is a number c such that v is equal to c times u. Let's put that definition in action. We're given the vector u, 10, 2, and a vector v, k, negative 4, where k is unknown, and we're asked that if we're told that u and v are collinear, what must the value of k be? So u collinear to v means there exists c such that v equals c times u. So k, negative 4 equals c times 10, 2. We're going to do the scalar multiplication thing. We're going to multiply the c into the vector on the right hand side. So k, negative 4 is equal to 10c, 2c. Now we go back to the definition of vector equality. Two vectors are equal if and only if their components are equal. So this means that k equals 10c and it also means that negative 4 is equal to 2c. The first equation on the right hand side there has two unknowns, a k and a c. We can't really do much with it, but the second one only has one unknown. It says negative 4 is equal to 2c. We can solve for c. Divide both sides by 2 and we get c equals negative 2. Now we can take that and plug it into the first equation. So k is equal to 10 times negative 2. So k is equal to negative 20. Once you answer the question, you could check, are they collinear? So is 10, 2 collinear with negative 20 comma negative 4. And it is if you can multiply 10 comma 2 by something to give you negative 20 comma 4 or comma negative 4. And yes, you can do that, so that means that we found the right answer. All right. Next example is just a repeat of one we already did. That's a common type of problem, so it's worth doing another one. We're given a vector u, and we're asked to find a unit vector in the opposite direction to it. So step 1, find length of u. So length of u equals the square root of 1 squared plus 2 squared plus 3 squared. So the square root of 1 plus 4 plus 9, which is the square root of 14. Now we do step 2, is that the new vector v is equal to minus 1 over L, so I should call this L for length, minus 1 over L times u. So minus 1 over the square root of 14 times 1, 2, 3, which is minus 1 over the square root of 14, comma, minus 2 over the square root of 14, comma, minus 3 over the square root of 14. That'll be our answer. Okay. That's just another one we just did. Okay. Vector translation. So this isn't a slide that you're going to have to use to solve problems. It's just a comment about some of the vocabulary that's used, some of the language that's used inside these problems, inside this course. A directed line segment can be translated from the origin, from having the beginning starting at the origin, to some other point. That is to say that not all directed line segments are vectors. Any directed line segment that begins at the point 0, 0 or 0, 0, 0 is a vector. But if we shift it so it begins somewhere else, it's still a type of geometric object, but it no longer could be classified as a vector. So we could take the vector v that's shown on this picture and shift it to the right and then down. So instead of being called the vector v, we would call it the directed line segment rs, where r is the point where the directed line segment begins, and s is the point where the directed line segment ends. It's just a curious notation for translating or shifting the location of that geometric object. So we'll have this weird notation show up, and we're going to treat these things as if they are vectors. We're going to do vector operations on them. We're going to find the length of the directed line segment rs. We'll find all types of related quantities, but they're technically not vectors, even though we're going to treat them like they are.